All right, and then the first step here, as also pointed out in the instructions, is to git clone our repo. So again, this is the repo where we also have the instructions here. And if you scroll all the way down, here again are the instructions, how to get here. And then it's really here, you can copy paste this link, which is cloning down this GitHub repo into that environment. So if you've done that, you should see here this workshop folder popping up on the left in this file browser. And then what we're going to do here, we click into that. And the workshop is structured as follows, that we're going to start here in the 0 quick start. And here you see a couple of Jupyter notebooks, and that is basically the workshop content for today. So starting with the first one here, which is just an overview really. And then we're going sequentially through those notebooks. So again, everyone that is in a demo account, feel free to walk through it with me. So first of all, here, this 0 notebook, I opened it already. So if you just do this with me, and here's really just another environment to play around in case you're not familiar with Jupyter notebooks. You cannot break anything in here. The first step you have to do is make sure the notebook has a kernel. So the kernel is basically powering the compute resources, the memory resources of this environment. So if you see the no kernel here on top, click here and then select the Python 3 data science kernel. This is the kernel we're gonna be using for this workshop. And it just takes a few seconds here. And then you should see that the CPU and memory resources appear, and you see the CPUs and gigabit here mapped. So when you see this, then the notebook has the compute resources and memory resources to execute the code. All right, and again, SageMaker is part of a larger AI and ML service portfolio that AWS offers. So here's a quick image where this fits in. And you might have heard or even worked with some of the AI services already that are listed here on top of this chart. Famous ones, probably Comprehend for natural language tasks, recognition for image recognition, object detection, etc. And a lot more. Sorry, I just somebody stopped my video, I think. So all of those AI services, and then in the middle tier you have the SageMaker family of services, as I call it, because in the meantime it's not just one capability. It's really a very powerful service that has a lot of different features, but also kind of functionalities in here to really help you get started, whether it's labeling data at scale, whether it's preparing feature engineering, sharing features, which you're going to see later here, running automated machine learning, and then also supporting the normal workflow here in building, training, and tuning and deploying your machine learning models. And as part of the workshop today, also some of the new capabilities that we introduced at last reInvent. I mentioned already the feature store, but also I think one of the big ones where we saw a lot of interest coming from customers and developers is around being able now to orchestrate all of the individual steps as pipelines. And we also have a notebook in here that you can run, which then shows you how to do this. All right, again, so this is just the overview. If you haven't worked Jupyter before, you click into those cells that have the code, and then just do either a Shift Enter, which executes the cell, or you can also run them in sequence. I normally do this, so you can do, for example, a restart kernel and run all cells. Again, only do this once per notebook because we're spinning up resources here. And we want to be frugal here. So again, here's just a couple of links to the Twitter accounts to show that you can also embed HTML code in here, which is pretty fun to see. You can also embed iframes in the Jupyter notebooks with that code here. And coming to the workshop content. So again, we're gonna build a text classification model today. And we're using the BERT NLP model, and we're using a pre-trained BERT model. So we want to be in 4 hours today. So we're not training a BERT model from scratch. This could take many, many hours, sometimes days. We're doing a shortcut, which is pretty popular. That is fine-tuning a pre-trained model to our specific data. And we're using reviews data, so customer reviews. And we want to build a model that is predicting the review given a text. So let's say I say, I love this movie. And then imagine you have a star rating from 1 being the worst to 5 being the best. And we want to have the model classifying the text into one of those 5 categories. So it's a multi-class classification task. We're using TensorFlow Keras today and fine-tuning the model then later, and then seeing how those predictions come in. And we're doing this as a pipeline. So in the next notebooks, I'm going to show you how to ingest the data, quickly register it with a service called Amazon Athena, so we can run queries on the data to explore it, briefly visualize it, and then we preparing for this pipeline and going to introduce you how you can check if there's any statistical imbalances in the data set that you want to like clear before you're using the data for the model training. And then we're showing you how you can prepare your features, meaning converting the raw review text into features that you can feed into the model. And then we're training it, and we're also going to evaluate the model. So what you can see here is this directed acyclic graph, this DAG, which is basically showing how the pipeline steps get executed. So we're going to pre-process the data, we're going to train a model, we're going to evaluate it. So we're going to check how the model performance is. And this really depends on the model and the use case. So in our case of text classification, we're just going to check here for the accuracy, the validation accuracy of the model. And then if this meets our threshold that we decide and we put in, then we register the model. And we're also creating a model here, which we can deploy as a REST endpoint to serve predictions. So this is basically the next couple of steps that we're going to do. And the last cell in each notebook here, you might be wondering, this is code that just shuts down the kernel again. So to release those compute resources back to the pool, we're just shutting down here the kernel. And this is all that this little HTML script here is doing. And when you run the last cell, you will see that the notebook kernel disappears and switches back to no kernel. And this is exactly as it's supposed to do, just to be frugal again here with all of the resources that we're spinning up. All right, again, so this overview notebook is just a brief introduction. And feel free, once you've been going through it, to just close it. And that's fine. All right, again, those of you who are in your accounts, feel free to start executing the following notebooks. So next one up is the 01. And in here, we're installing a couple of dependencies. So we're checking for the Python version, and we're also pulling in a couple of SDKs. So for example, the SageMaker Python SDK to be able to interact with the service here from our Jupyter environment. And another service or part of the SageMaker family is SageMaker Debugger, which lets us debug and monitor really the model training. So with Debugger, you can capture tensors during the training to analyze if there's, for example, what's happening if loss is not decreasing. And you can also use that to trigger actions. So for example, if you're training the model and the rule says, well, I see that the loss is not decreasing anymore, or you're starting to overfit your model, you can actually say stop the training right here, because it doesn't make sense to wait 2 more hours potentially if I'm already starting to overfit. So really, really powerful. And Debugger also lets you monitor the infrastructure resources. So for example, it can analyze whether you're hitting any bottlenecks, for example, CPU bottlenecks in your instances that you're using, or GPU bottlenecks. And it gives you also actionable tips. So let's say maybe increase your batch sizes for better efficiency and use of infrastructure resources, etc. All right, and also, yeah, pulling another here in, which is SageMaker Experience, which we can use to log the individual experiments, and with that being able to, catalog the different settings that we're using, and being sure to kind of catalog and being able to compare the different, for example, model runs that we're doing. All right, and then we're also installing a couple of conda install here. For example, we're pulling in the pytorch package. And then also TensorFlow here. We're also using Hugging Face. So for those of you who are not familiar, Hugging Face is a popular NLP open source library, and they offer a lot of transformer-based BERT models pre-trained. And we're going to use one of those transformer models for this purpose here. So we're going to use the distilled BERT, which is a distilled efficient variant of BERT. And we're pulling this in here from the open source Hugging Face library. So this is why we're installing transformers here, the Hugging Face library. And then to interact with services, for example, with Athena, there's also SDKs. And here we're pulling in the PyAthena SDK. And in some cases, the workshop also has in the larger code base Redshift examples. So for example, to interact with Redshift, you can pull in an SDK called SQL Alchemy. And we're installing a couple of little tools like zip, for example, which is not part of the base kernel. So we're just making sure to add everything that we need. And also here, matplotlib and seaborn to visualize. All right, so the notebook will take a few minutes, as especially PyTorch and TensorFlow are a little bit larger to pull in. So just give it a few minutes here as it installs those libraries and the SDKs. And then we're just doing a last check here, Python version and a pip list to make sure everything got installed. And we're also just setting here a local key value store entry to say, to check that we actually executed this and set up all dependencies. So if you see the %store command here, this one is just a local key value store used in Jupyter. This is a little bit of Jupyter magic here, as it's called. And as you can see here, if you do the %store, this will really just show the key values here in the notebook, and it's saved locally in this environment. But this gives us the ability in the next notebook to retrieve those values and check. And it's coming in really handy as we save a little bit of information, as you will see here, as we're building up our pipeline. All right, and last cell again is shutting down and releasing the resources. So once you run the last cell, you will see that the notebook flips again to the no kernel. All right, so this is just a few more setup steps here. So I'm going to close this. And if you open up the second notebook here, register per K glue Athena, this is now getting into the first steps. And what we're doing here is we're registering our data set with Amazon Athena, and also making sure that the metadata, the schema information, is stored in a data catalog. And in this case, we're using the AWS Glue data catalog. All right, so let's see what's happening, and feel free to run this notebook to also get this executed. I already executed this before, so I can show you the results. So feel free to run the notebook if you're following me along here in your accounts. All right, so the first step that we're doing here is we're registering our data set. And as I said, we're using a customer reviews data set, which is hosted in a public S3 bucket. To interact with the services, here you can see the first lines of code. We're importing the Boto3 Python SDK. This is the general AWS Python SDK to interact with the services, and also the SageMaker specific SDK. And we're setting up here a couple of information, for example, the current session we're operating in, the default S3 bucket that is set up, the current role, the execution role, that is the IAM role that gives us permissions to do all the things in the accounts, the current region, and the account ID. And this is kind of the boilerplate code we're gonna pretty much use in every notebook. So this is really just to have all of the information needed to interact with the services. All right, then more specific, here we're importing the PyAthena SDK. and specifically the connect object. And we're also importing pandas to work and crunch the data here. All right, and here you can see the dataset columns that our dataset has. So it contains information about the e-commerce marketplace, whether it's, for example, a US-based marketplace, random identifiers for customer IDs, a review ID, product IDs, etc. And again, this dataset really shows customer reviews of products, and we're going to use that to build this text classifier model here to predict the star rating, which is from 1 to 5, given any input review text. All right, we're setting up. This is really just a temporary cache directory in S3 that Athena uses to store the query results that we're going to do here in just a bit. And again, Athena is a service that helps you to run interactive queries, SQL queries on data stored in S3 without the need to move the data anywhere. So this is really, really powerful, especially if you have a large data set that you don't want to move into a database, that you don't want to move into a data warehouse, just for being able to query it. So Athena is really, really powerful for that use case, running SQL queries on data stored in your S3 bucket. And what we're going to do, we have to define the schema to be able to use SQL, right? If you recall SQL, we're going to do a a select star from database and table. So for that structure and syntax to work, we have to define a database name and a table name. So Athena comes with a default database. That's the one we're going to use. And then we're defining here a table name. The dataset we're using here comes as in two different file formats. One is TSV, which is tab separated, similar to comma separated CSV files, in this case just separated by tabs. So very structured format. And the other one is Parquet. And Apache Parquet is a columnar optimized binary format. And Parquet is really, really helpful if you're running those analytical queries, like SQL queries, where we're using filters such as where the product category equals, for example, books. And the power here is that Parquet is optimized by column, so we can store the column information together. And if we're doing those SQL queries where we're saying like where the product category equals or where anything equals, we can very efficiently query only the relevant data. All right, so we're setting that information, and then we can use the PyAthena connect to connect to the Athena service. So here we're just specifying the region and our S3 staging directory. And then we can almost start writing SQL queries here. So here's one example. And this SQL query here, I just show you here the printed command. This one creates an external table, and this is basically the metadata table to register the data set. And we're doing an external table because we're pointing here to a location in S3. So here you can see where the data set is stored. This is the public S3 bucket. And what we're defining in here is really just the schema. So all of the columns and the data types that are part of this data set. And then we're partitioning, and this is particular to the Parquet data. So again, with Parquet, you can partition, and just think of a partition as a subfolder. So we're basically storing that information categorized in folders by the product categories, such as books, such as digital video games, digital software, etc. Whatever the e-commerce store has as categories. And then here you can see we're saying this is actually Parquet format. And here's the S3 location. And what we also need to do is then to log the individual partitions. So here we're running another SQL command, and this is really just analyzing, reading in, and then building the partitions. And we can fire up those statements with the pandas read SQL command, actually, where we pass the statement, the SQL statement, and this connection object. All right. And we can check if this command executed successfully. So we just run another SQL command, the show tables. And we can see here that our table shows up now. And we can check also by running a sample SQL query. So let's just run one. Let's do a select star, always famous, from this database default, and then from our table that we created, Amazon reviews per K, where the product category equals digital software, and that's limited to 100. And we can fire this up again in the pandas read SQL, and here passing the SQL statement, the connection, and then showing here the results. And just to again recap the great steps that are happening. So we do have the data that we're using stored in an S3 bucket. And this could be potentially, not just gigabyte of data, this could be petabyte of data, this could be exabyte of data, depending on the data you want to use, right? And as a first step here, as a data scientist, machine learning practitioner, we want to be able to explore the data, right? See how the data looks like, see how, if there's anything interesting in the data, see how the distribution of the data is, etc. So we want to be able to fire up SQL queries against the data, but without having to have, to transform the data, load it anywhere, because we don't want to move potential petabytes of data, right? And this is where Athena really, really is powerful. So all we did here is really just register the schema information as metadata with the Athena service. And Athena leverages a data catalog, which is coming through AWS Glue. And with that, we can then use the SQL syntax to query this data in the S3 bucket. And here we can see the results. So this is sample reviews here from the software category of reviews. All right, so just checking here that everything is created correctly. So the table is created, and then we're storing that information again in our little key value store here with that Jupyter magic command. And if you're curious, so here we are also giving you a link to see the Glue data catalog. So if you click on that, it will take you to the console and specifically to the AWS Glue service. And in here you can see at top, here is the data catalog mentioned, and we can see the databases. So the default one is the one we've used here for our table. And if you click on the tables, you can see here the Amazon reviews per K. This is the one we just created. And if you scroll down, you can see here the schema. Again, we didn't move the data anywhere. We really just registered the metadata, the schema information. And here you can see, for example, review ID, in this case is a string. The star rating, 1 to 5, is an integer, etc. And this is the catalog which then Athena uses if we're running queries to understand where to find that information. And again, this points to the S3 location where the data is stored. All right, coming back here to my notebook environment. And this was the register data notebook. So I'm going to close here, making sure the last cell shuts down the kernel. And then closing this notebook. And we're coming up, sorry for the scrolling here, to 03, which is visualizing the reviews. And I might just quickly check in here with Chris how we're doing on the question side. If he can hear me.
Hello.
Muted. Unmuted.
Hey there.
Yes.
Yeah, so the rest of the team is answering questions. I just got off a call, so I'm going to try to reload a new link here that I'll be posting. So we should hopefully get these in the next 30 to 45 minutes. So yeah, let's just keep moving.
All right, perfect. Thank you. All right, and I see here some people asked to slow down a little bit. So what I'll do, I'll just quickly recap. It's not really big things that we have done here. So I want to make sure we can spend a good amount of time on the actual model pipeline steps. So I'll do a quick recap here for everyone who might have just missed a few of the steps. So what I've done here is really just installed a couple of Python and framework libraries. So this was the setup notebooks in 01. And the real thing I've just done here in the 02 notebook is we have a data set we're going to use. It's containing customer reviews from products. So for example, I loved the movie, or just bought a book, or really enjoyed the book, or I bought this, I don't know, this new clothes and they don't look, I don't like them, right? It's customer reviews. And the goal that we're going to do here is building a text classifier that classifies any review text we're sending into a star rating from 1 to 5. So again, we set up a couple of SDKs, not too exciting here. And in this notebook I've just showed you, we registered the data set that is in S3 with a service called Amazon Athena. And Athena is an interactive query service, again, that lets us run SQL queries on data stored in S3 without moving the data. And this is pretty much all we've done in this notebook here. So you can see here the schema information of the data set. So it has review IDs, customer IDs, product IDs, everything you would expect. And the command to create this schema metadata table is shown here. So this is the SQL command we've run. And here you just really point out the columns and the data types. And in this case, we used Kdata, which is optimized for columnar-based queries. And we've said it's Kdata, and we pointed it here to the location in S3 where the data is stored. And we loaded the partitions, and that's really just a step that's extra if you're working with Kdata and partitions. So we loaded the partitions, and then we have this table that I showed here, which is really just, again, showing the schema of the data set, right, which we just created. And Athena is based on Presto. So you might be familiar with Presto, I'm not sure. So Presto is an open source engine that does exactly that. So giving you the ability to run those queries on very large data sets. What it does, it takes your query, it simplifies it, and it distributes it across the data set to be able to very fast respond back with the query results. And this is basically where Athena is built upon. And then the other service here I threw in the mix is AWS Glue. And in this play here, Glue is basically providing the data catalog, which keeps track of those metadata tables. All right, so this was everything we just did in this notebook. And now we have this metadata and the data registered. And this means we can use Athena now to run queries on the actual data set, as we've done here. So we've just done here a sample SQL query, select star from, and we see the data results. All right, so much more interesting are the next notebooks. So if you want to open up 03 Visualize Reviews dataset with me, and in here, we're now using the data that we registered, and we're gonna answer a couple of questions here on the data set. And the way this works, if you want to do, you can do a kernel restart and run all cells, which will execute all of the cells here in this notebook. So you can get the execution going here while I walk you through it. All right, so I've already run the notebook. Make sure that you do have a kernel assigned. If you do see a no kernel at top, again, make sure you click in here and select the Python 3 data science kernel. And you should always in each notebook see here the vCPUs and the gigabit of data for memory available. And that means the notebook has those compute resources. All right, so if you see the Python 3 kernel, you can execute and run the notebook. And again, we're asking a couple of questions to explore the data. And this is really useful if you're preparing for the model training, because you want to understand your data and you want to understand which preparation steps you have to perform, right? So again, here, the first lines of code is really just, again, importing the SDKs, SageMaker and Boto3, and setting up here also, again, session, bucket, role, and region information. This is really just the boilerplate code used to interact with the services. All right, then more specific, we're using NumPy, pandas, seaborn, and matplotlib. And these are really very popular Python libraries. NumPy and pandas really kind of to work with data, to crunch data. And then seaborn and matplotlib are primarily for plotting and visualizing in those Python notebooks. And here's one little trick. If you're working, for example, with a MacBook display, Retina display, there's actually a setting which you can use to tell Matplot that it's optimizing the plots, the visualizations here for a Retina display, which really helps in kind of having nice, sharp figures showing up. All right, then we're just checking here with this store, like the Jupyter Magic Store command, that we've completed the previous notebook. So again, we're using this to store information and retrieve through different notebooks. And the previous one just saved that we registered the data. We're making sure that is actually the case. So in case you're seeing a printed error here, you probably haven't run the second notebook to finish. And hopefully this should turn true and okay for everyone. And then we're just here again pointing to that database and the metadata table that we created. We're pulling in the PyAthena again and the connect. And also here pointing to an F3 staging directory for Athena. And then we can start with the queries. What I also do in here is just set up a couple of seaborn overall parameters. So like the font style to use in the visualizations, the grid colors, figure face colors, title sizes, etc., to have it set up just up front for a couple of the plots that I'm doing in this notebook. And I'm also showing some helper code here, so to show values on bar plots. And yeah, just a little bit of a helper code here for the visualizations. Not too exciting. All right, so let's focus on the data exploration. So what I'm doing here is I'm starting with a SQL query. So I want to have an answer to the question, which product categories are the highest rated by average rating, right? Are the books the highest rated? Are maybe digital software the highest rated? And the way you can answer this question is by creating a SQL query here. So this is what I'm doing. And I just show you the printed one here that's easier to read. So I select the product category from the data set. I calculate the average from the star rating and use that as average star rating from this database and table where the product category is in. And I just limit it here to the 3 categories. So I'm going to look into the digital software, the gift card, and the video games. I'm going to group it by the product category, and I'm ordering it by the average star rating descending. And then here you can see I fire up that query again using the pandas read SQL, which comes in pretty handy, passing in here the SQL statement and this connection to my Athena in the region. And then the result here is pulled into a pandas data frame. And you can see here the results in this table. So for example, in these 3 categories, gift card is the highest rated with an average of 4.73, digital video games 3.83, and then digital software 3.53. And here is the visualization code. So it's even easier to spot any of those, data characteristics if you're visualizing. So that's a great way to explore the data. And what I'm doing here and showing is how to create a bar plot. And I'm using the seaborn library, creating a bar plot, and then just passing in here for the Y and X axis, the labels. I'm passing this data frame, which contains the results from the SQL query as the data. And then I can, for example, add a couple of extra information like the title for the plot and the ticks. Those are basically the markers here on the x-axis, and say label it as a 1-star, 2-star, etc. Putting in additional labels, and then I can do the show on the matplotlib, and you can see here the visualization coming up. And we do it here for the 3 categories just to be quicker in generating those visualizations. And it's really interesting if you run this across all of the data. So to just make this convenient, I've executed this before and put in here a screenshot. So here you can see the results if you were to run this across all of the different categories. And we can see indeed that gift card is the highest rated with 4.73. And then you can see here all of the categories that are contained in this data set. And also you can see the bottom one here, digital software, is indeed not the best rated category with a 3.5, for example. And again, the purpose of this visualization is really to kind of show you how you can create powerful visualizations to explore the data. The average star rating here is kind of just an interesting one, but what's also very helpful is to see how many samples do those categories have, right? So the next question you see in here is which product categories have the most reviews? And this one helps you if you're building up your training data set for the model development, because you want to know how many samples each category, for example, has in order to, package together a trained data set, which might not have the millions of samples because you want to maybe quickly prototype. You might just need a couple of maybe 10,000s of samples. So you want to have an understanding maybe which categories you can pick here and how many samples are in each. And again, we're starting here with a SQL query. So this one is select product category. You're counting the star rating. So this is giving you the count. And then from our table, which contains the information of the schema and where to find the data. And then we're grouping here by product category, and we're selecting again the 3 categories here as just a subset. And then we're also ordering by the star rating count, descending. And we can see the gift cards, for example, have roughly 150,000 reviews, video games 145,000, and digital software 102,000. So a good amount of review samples to start building a model and prototyping it. All right, and you can also visualize this here. So again, I'm doing here a bar plot. So similar code from seaborn. Bar plot is already a built-in capability. And you can see here again, the X and Y axis labels that we're putting in, passing the data, and setting a little bit here of the markers, the scales, etc. So I'm not going into the details of every visualization code. Feel free to have a look at the notebook if that's of interest. But I want to focus here on a little bit more of the relevance as well and how we can use that information. So if we're plotting this, here we can see the 3 bar plots, gift cards with 150,000 reviews almost, and then the other ones slightly less. And again, this is more interesting if you run this across the whole data set, as you can see here on the screenshot. So in our case, the data set contains indeed almost 150 million reviews. And you can see here that books are definitely the ones with the most reviews. And if I scroll down here to the axis, you can see almost 20 million samples are in the books category. So we do have 20 million review samples if we need, if we pick, for example, this product category. And then it's going down sharp here, and you can see the ones we picked for this workshop, just to be able, to not have a training time of too long. We've picked categories here we're going to work with that are more in the 100,000 of samples, which is good enough to actually our task of fine-tuning the model. So for example, you can see here the digital software 100,000, video games and gift cards. All right, we do have a couple of more queries in here. Feel free to have a look. I'm not going through all of the 12 ones today. We're doing some visualization here, for example, when categories got introduced at the marketplace. So you could maybe grab if the dataset contains a review date. What we're doing here is looking for the first review date in each category. And we're just assuming that this is marking basically, when the category got introduced, for example, on the marketplace. So this one shows here how you could do a line chart here based on time and date information. Another one here is a breakdown of ratings per product category. And I'm going straight to the visualization here to show you what we can learn from that. So there's a little bit of more code needed. But the result here is that I want to plot, the distribution here. For example, how much percentage of the samples are 5-star ratings, how many are 4-star ratings within the category. And if you recall, we're going to train the model to predict those star ratings. So the star rating of the training data is basically our label. And you can use that information to understand how a baseline for the data looks like, right? This comes in handy if you train the model, deploy the model later into production, and you want to understand when there's a drift in the data, when there's a data drift happening, and you suddenly see a different distribution, for example. And if you've been working in the space, that might sound familiar. There is, for example, the label shift. There's also concept drifts happening. So whenever the statistical characteristics of data change, you speak of a drift, right? The covariate drift, if the input features change, the label drift, if the label distributions change, and the covariate, the concept drift, if the whole concept of the prediction, so the input features to the labels change. And so this is helpful here, this query, for example, to give you a good understanding how the distribution for the label look like, right? So in this case, you see if suddenly the model predicts way more 1-star ratings for gift cards, you certainly know that there's something happened, because normally this comes up here to close, I think, 85% of 5 stars as a distribution. So all of those visualizations, you can get really some good insights and help you, as I said, in building the model later. All right, even fun if you visualize it here across all of the categories. So this is how this eye chart looks, Len. And yeah, feel free to revisit the code maybe later if you're interested in how to run this. And we have a lot of more queries in here. Again, I won't go through each of them. Maybe one more. And here, for example, we look for the review count per star rating. So how many reviews do we have for the 5-star ratings? How many reviews do we have for the 4, 3, 2, 1-star ratings? And you can see the results here plotted. And it's pretty much similar if we run this across all of the data available. So what this tells you is that there is an imbalance in the number of samples you have available, right? So there's way more 5-star positive reviews available than there is negative reviews. So this is an imbalance we're actually going to handle in the next notebook here to help you show how to mitigate those imbalances. All right. So you can also check how the star rating changed over time. So we do have another line chart in here. And this is kind of interesting from a business perspective. So if you plot this per category, for example, you can see if there's any category that had a drop in customer satisfaction. So this would be something the line of business owners would be interested to visualize and obviously see early on to be able to jump in and see if there's anything they need to resolve. All right. And I'm just going to scroll down here to the very last query. So this one. And this one is particularly interesting, sorry for the scrolling, to help us prepare for this NLP model training that we're going to do here in just a bit. So one of the hyperparameters, the model settings to fine-tune a BERT model, an NLP model, is often the maximum length of the input tokens. And don't worry, we're going to explain this concept and the ideas in much more details in the following notebooks. Right now, just think of it as a hyperparameter you need to define. And you might not have a good idea. So how many tokens, and think of tokens roughly for now as the number of words, right? When we create those features for the model, we need to transform the raw text into those model-specific embeddings. And one step in doing this is basically tokenizing the words. For now, just think about it as the number of words and how many of those you will pass as one sequence to the model. And we can actually explore this here in the data as well. So here is what is the distribution of the review length, aka the number of words. And this is pretty easy. So you just take the review text and you split it here by the white space, so by the to get the individual words, and then calculate the cardinality on it, right? So how many individual words do I have when I split here by the space? And this gives the number of words. And what you can do with it is you can calculate percentiles now. So we're doing this here on this data frame, which has the number of words. We're calculating the percentiles, and then we're plotting this as a histogram to see the distribution. So if we look at this chart, this helps to understand what's happening. So we're calculating the number of words across each review, and then we're seeing how the distribution looks like. And if you look at those percentiles, you can see the shortest review has just one word, right? So this might be a great or an okay. And the longest review, the max here, has over 5,000 words. But what we want to find really kind of, is a value that is capturing most of the reviews without really taking into account every single one that is really, really long. And if we plot this now, this is where we have this assistance in choosing this value. So again, if I look at this table, 80% of the reviews have 63 words and less. So if we pick here, for example, 64, just as a number to the power of 2 is always kind of the preferred choice in computer science, we can see that we cover 80% here of the reviews. And there's a very long tail here with reviews that have more. But generally speaking, if we capture 80%, this is good enough for choosing this parameter, as we will see later. So this is what we're going to do. And again, don't worry if you don't understand why we need this right now. Chris will walk you through that in a bit here and explain in much more detail why this is an important parameter. All right, and this was the visualization. And I would say I do one more notebook, and then we're coming up to our break time. And I'm going to take a break so everyone can catch up on those things. All right, so making sure the last cell again is shutting down my kernel. All right, so just a quick recap again. I know I'm moving fast, but again, this is kind of the setup steps of ingesting the data, exploring the data. We visualize the data. And we have a few more exciting steps here coming up then after the break that we take at 11. That is showing then how to step into the feature engineering. So we're going to transform the raw data into those embeddings that we can use with those NLP models, such as BERT. And then showing you how you can do this fine-tuning of the model. And then we're putting down all those steps together in a SageMaker pipeline, running the pipeline. And then we're evaluating the model. and doing some further analysis. So there's much more exciting tasks coming up. What we've done so far is, again, we registered the data set that is sitting in S3 with Athena and created the data catalog entry. And the visualization now was just using SQL queries via Amazon Athena to show you how easy it is to run those queries, and then also to give you an idea how you can visualize those in the notebooks. So what I want to do now, before we take the break, is running the 04 notebook. So if you open up 04 and execute this notebook, so what you can do is restart kernel and run all cells in here. And here we're using one of the new capabilities of Amazon SageMaker called Amazon SageMaker Clarify. Clarify helps you to detect imbalances in your data. And we will also later on use Clarify to detect imbalances in the model, looking at predictions. So when I talk about imbalance, you might also heard the term bias, right? And bias is basically a statistical imbalance, could be either in the data set, and we will see how this looks like, or it could be in the way the model performs and does predictions. And if you remember that little visualization I showed you where we saw we have way more 5-star ratings in the data set than we do have 1-star ratings. So this really shows how those imbalances could originate from, right? From having this imbalance across those classes, for example. There's a lot of research going on in the industry around how to detect imbalances, how to detect any biases in the model and the data sets, and how you can mitigate them. So if you want to learn more, here I linked a paper from Amazon Science, which discusses the tool here used, how Clarify can help in much more detail to detect those imbalances. So feel free later on, if you want to understand this in a little bit more detail, to read this paper. It's a really, really nice one. And briefly, again, this whole area of talking about the statistical biases and imbalances, there's a lot of new terminology that comes with it. And I've put in here just a few definitions to make sure when we're using those terms, we all understand what we mean with it. And I've also put in here a link to the documentation in SageMaker that goes into much more detail about this. So for example here, and I already introduced the term, when we talk about the bias, what we're referring to is a statistical bias, which means an imbalance in the training data, for example, or the prediction behavior of the model. And this could be really, you know, given any imbalances. In our case, we're going to have the imbalance of the different product categories. For example, we saw that the gift cards have way more 5-star ratings than, for example, the software category, right? And traditionally, you would look at also different, maybe more sensitive groups. So for example, if you're looking if your model or your data set has just more samples of maybe people of a younger age versus people of a higher age, etc. And this is just another example of a statistical imbalance that could lead to the model predicting different given that imbalance it was trained on. And a way to measure this imbalance is using metrics. And those bias metrics are functions, mathematical functions that return numerical values. And they can give you an indication of how much of an imbalance is in the data set. And they get summarized, hopefully, in a report. And we will see a few examples here in this notebook, actually. The label is, as we're familiar with, the label in the data set. So basically in supervised learning, where we train the model with information that has already the example answer. So this is also called the target sometimes. that we train the model on. In our case here, the label will be the star rating of that review. And then to detect if the model, for example, is favoring one specific category, you would have to tell it what's the favorite result. And in this case, in the reviews, obviously a 5-star rating, so the best rating is a positive result. And if it's a 1-star rating, that's just what we say is a negative result. If your use case is, for example, approving credit loan requests, and I get the loan approved, so the yes would be the positive. If I get the credit loan declined, that would be the negative one. And then there's one more term, which is called facet. And facet is, just think of it as a column in the data set, or if you want to call it the feature. And in this case, again, we're going to use product category as a facet. That we're going to check if there's an imbalance. And then the value is just one of the values of that column. So for example, in our case, gift card, software, video games, etc. All right, and we're coming to the more complex ones here. So I said you can calculate those imbalances, statistical biases with metrics. And I've also summarized here, and feel free, again, this is a long and broad topic, to revisit this after the workshop. I put in here a link, again, to the documentation, and I just want to briefly show you maybe one example. So we can use SageMaker Clarify to detect those imbalances. And the way Clarify does this is by calculating a number of those bias metrics. And one of them, a simple one here, is this class imbalance. And here you can see we're changing now the terminology to use this facet terminology. So that's why it's important to understand. And again, facet is really, think of it as a column in the data set. So in this definition, the class imbalance occurs when a facet value, let's say gift card, has fewer training samples when compared with another facet, let's say software in the data set. And all of those metrics, you can find here the mathematical function how to calculate, right? So the class imbalance here is taking the number of samples from the one facet value, let's say gift card, and subtracting the number of samples from the other categories and the values that are present, and then divided by the number of samples as a sum. And the result of this calculation is a value in the range of -1 to 1. And this is with most of the metrics here. And in pretty much all of the metrics, unless it's otherwise stated, that values closer to 0 indicate a balance, and a value closer to either -1 or 1 indicates an imbalance, right? And the positive is really looking from which facet you're coming from. So again, with that formula, if you have a positive value, that indicates that the facet A has more training samples compared to the rest. And if it's a negative value, that indicates that the other facet has more training samples, right? So again, just short to memorize, anything close to 0 means more balanced, and everything closer to 1 or -1 means imbalanced. And again, there is a few metrics that can be used to detect those different kind of statistical biases and imbalances. So feel free, I'm not going to touch all of them, but feel free to revisit if you're interested in this topic. I've just put in here a quick definition of those. All right, and how can we do this now? I want to see this metrics report, right? So again, we're just using our boilerplate code here, pulling in also matplotlib for a little bit of visualization. And we need to give it now the data set. We're going to analyze and check if there's any statistical biases, class imbalances in here. So what we're going to do here, and I just put in here 3 categories. So I'm using the gift card category, the reviews from digital software and video game, and I'm concatenating those into a data frame here. Same look and feel here of the reviews, and I'm plotting them here together to see actually that we do have quite an imbalance, right? So I plot all of the 3 categories here together, grouped by the star rating. And you can see here, no surprise, right, that all of the 3 have much more 5-star positive values than they do have samples here for the negative classes. So we can spot right away that there is an imbalance in the data set, right? All right, so let's see how the tool can help us to calculate this with the metrics as well to have more insight. So what I'm doing, I'm just exporting this data frame here, which I constructed into a CSV file. And this is really just for me to kind of crunch the data a little bit. Obviously, if you have the data already sitting somewhere, you can use that. I'm just doing a little bit of construction here. And then uploading it to S3 into our S3 bucket. All right, so the fun part is now, how can I use SageMaker Clarify to help me analyze the data? So what you can do here, as you can see, is from SageMaker, import Clarify. And I'm just configuring here a couple of parameters. So one of them is, for example, where to store the generated report. So this is an S3 path. And then, yeah, so the name, and then here the path. And then what I'm doing is I'm configuring here Clarify with the data config. So the data path, where to find that CSV file that I uploaded, and then here where to store the results. And you also have to pass the label information. So this is telling which one of the columns in the data set is my label. In our case, we're using the star rating. And then we just have to provide a list of the column headers with for the other columns that are present in this data set, and then which type of data it is. In this case, it's text data, CSV data. All right, so we know where to find the data. Next, we need to configure the actual Clarify configuration here. So one setting here is we have to tell the positive label. So again, we're choosing, in our case, for the product categories and the reviews, the 5-star, 4-star ratings as the positive ones. And the column to analyze for, the facet, is the product category. And the group name here is really just used for one of the metrics that needs to group the data, again, by one of the columns. All right, so with that setting, we can move forward. And here you see now one of the advantages of using SageMaker, and also in particular what's called a processing job. So just imagine our CSV file is not too big, but imagine you have, again, a large data set sitting in S3, and you want to run this analysis over this large data. You can use SageMaker Processing Jobs to basically perform those analysis or feature engineering data processing steps. And the way it works is you can specify basically a number of cloud instances and types to execute specific code. And in our case, there is a predefined container image, basically. So this processing job is already configured with the code to run this Clarify SDK or the Clarify tool. And we simply have to say how many instances and of which type. And then what SageMaker will do, it will start this processing job, basically the number of instances you specify here. And this one has already the code to execute. And we just give it the pointer to the data set. And then the data set will get analyzed. All right, so this is really kind of the infrastructure part. And the nice thing with SageMaker is that you don't have to take care of the creation of those instances what we often call the undifferentiated heavy lifting. So we just specify do 1 instances or do 5, depending on how much processing power you need. And SageMaker will spin up the instances, run the job, and then when it's finished, also terminate those instances again. All right, so we do have the infrastructure defined. We do have the data set defined. We know what to look for. And the next step here is to start it. So on this processing job, we can now say run pre-training bias. And we're passing in here the data configuration, which is pointing to the data that we created. And we're also pointing to the bias configuration. Again, this is choosing the product category and the positive labels of 5 and 4. And in the methods here, you can specify which of those bias metrics you want to calculate. In this case, let's just calculate all of them. And with this, SageMaker is starting now in the background a processing job to analyze the data. And again, we put in here deep links, so you can click on those deep links. And those take you to the console and specifically to the SageMaker Processing Jobs. And you can see here the job that you just started. In my case, I executed the notebook before, so I do have this one completed. If yours is just running, it will just take this one here roughly 4 or 5 minutes, so rather fast to execute. And again, you see here all of the configurations. So 1 instance, the image that is used, and the instance type here, the M5X large. So again, just a quick recap, those images. This one is a pre-built image that already has the Clarify SDK loaded and all the code needed to execute. So in this case, it's really, really simple to use those processing jobs. And in the pipeline for the model, we will show you how you can also use this processing job construct to run, for example, the feature engineering for the BERT model. So processing jobs are really kind of very flexible to do very different things. You can analyze data, you can pre-process data. And in this case, we used it to execute this data analysis step to check for those statistical biases. All right, there's also a link to the CloudWatch logs, which is where everything gets logged in AWS world, all the logs get sent to. So in case you want to see on a more fine-grained level what's happening, you can check out those logs. What I want to show you here is, for one, the F3 bucket where we store the results. Again, this is something we specified. And here you can see, if I zoom in a trillion times, the report that is generated and the configuration, everything is stored in here. And we're pulling down this information now from the notebook to actually show you the report. So going back to the notebook here, if this processor is running for you, this will just wait for the actual job to execute. And I think mine here actually executed, but I think the UI here didn't update. So what we're doing here in those following cells is we're downloading those results from the F3 bucket. And if those cells run, you would have here a link. Basically what we're doing, I can also pull it up here, is we're storing this here in the local folder. So let me see if that one actually, maybe I open it here. So this one, I think I ran it before, so this one type, yeah.
Yeah, before we get too far, I just wanted to make a big announcement that I do have a link. So if you would send me a direct message and I'll share a link to get you the account. We already have quite a lot of people that I've been pinging on the Slack, but there's still people that I think are just listening. So if you do want to get your account, we are also going to keep the accounts up for 1 hour afterward. And to let you catch up. And yeah, Anja, like, let's take a break here real quick to let people get caught up and to get them spun up.
Yeah, should we right now? Otherwise I would have done at 11.
Yeah, so yeah, just finish this section, that's fine. I just wanted to make the announcement before people start dropping off before the break.
Yeah, sure. So let me just quickly wrap this, and then we're taking the break, and then I think we have 15 minutes scheduled for the break, so we can make sure everyone that's still missing an account gets into there. And then, yeah, perfect. So we're keeping them up and running after the workshop for another hour. All right, so let me just wrap here, and then we can start after the break with the pipeline. So what I've downloaded here is the Clarify report, and it should also show up in your notebook if you run it. Mine just timed out because I started it like I guess 2 hours ago. So in the dev3 bucket, you see all of the files. So I just downloaded here the report HTML, for example, and opened that. And this one here is the result from Clarify. So here you can see that we analyzed the product categories. And here, for example, the value gift card. And we also looked for the star rating as the label and the positive values 5 and 4. And what happened here is now that Clarify calculated those metrics that I showed you, for example, a class imbalance, difference in positive proportions, labels, etc., and all of the other ones that help you to detect those statistical biases. And we see the calculated results. And again, everything closer to 0 is closer to be balanced, and everything closer to a -1 or a +1 is an imbalance. So we can see that we do have statistical imbalances here in the data, and those ones we can obviously address and then see how this works out. And let me just show you here real quick the rest of this notebook, and then we're taking the break. So what we can do now is, and the visualizations didn't show up here. So basically what we can do is make sure we're balancing the samples across all of the categories as I showed before. I think the image, this one was shown here. So there's techniques to oversample and to downsample. So basically what we're doing is we're cutting down to the lowest number here of reviews, so we can balance the same number across all of the categories. This reduces the number of samples. So another approach is to basically upsample, where you generate additional samples to match the highest. In this case, we've done a second one where we just really sample down, and then you can rerun, for example, Clarify, and you can see if this helped to balance a little bit better. And this gives you really kind of a good way to mitigate or detect and then help understand those imbalances and take actions. All right, so this is a short intro to the SageMaker Clarify tool. And again, I've put in links here. So this could fill a full day of content and workshop. So I just wanted to give you the quick intro here and how to get started using it. And feel free to read here about more details with the links I've put in the notebook. And with that, let's break for, should we do 15 minutes, Chris? So everyone has a chance to get into the accounts. And then you don't have to worry if you haven't been doing those notebooks. You can start after the break with the notebooks when I hand it over to Chris as well to get going. Just make sure that you're running the setup dependencies one, the 0-1. That one is required, but then you can pretty much catch up with the later notebooks that we will be doing and showing then. And we will start after the break with the feature engineering. So we're going to create those embeddings from the review text, and we're going to show you how you can store and share those in a feature store. So pretty exciting, one of the new features that got launched at last reInvent. And then we're introducing you how to do the fine-tuning for the BERT model. And then we're building the SageMaker pipeline, which will execute all of those steps together. All right, so coming back here to the workshop, and I'll just do a quick recap of the first half. And then we're going to the exciting second half, where we're actually now getting into the actual model preparation, feature engineering, training, and the pipeline, which I hope everyone is waiting for. All right, if you're just gotten to your demo account, follow the quick setup instructions. Basically go into the console, SageMaker Studio, clone the repo, and the only notebook which you have to run is 01. So just make sure you're executing here the setup dependencies, which is installing the SDKs and packages that we need. Okay, so you don't have to literally go fast through all of the notebooks here that I've just showed in the first half of the workshop. Feel free, we're keeping the accounts up for another hour after the workshop to revisit them, of course. But if you just want to catch up here and follow from the 05 notebook, that is fine. Just run the first one here, which is doing the setup dependencies. All right, so, and let me just double check here that those notebooks executed. Yep. So what we're going to do next here is I'll walk you through how we can prepare our raw text for BERT features. So how to convert the text into embeddings that the model understands. And then we can start training the model. And if you remember in the beginning, I mentioned that we're not actually training the model from scratch, but we will do a fine-tuning. So I'm gonna show you how to do this as well. And then we do have the actual pipeline that we're gonna build up that is then orchestrating all of those steps. So from the processing to the training to the model evaluation. And we'll also do have a few notebooks here after the pipeline to run another bias detection on the model. So you can also use SageMaker Clarify to detect model biases. And then you can also use it to do explainability. So we can do a feature importance to visualize which feature of the input features contributed to a model prediction. So also really, really good to know. And this uses SHAP as a method. And then at the end, we will also deploy our notebook. So, and then serving real-time predictions. So this is kind of the outlook for the second half of today's workshop. So hopefully you're as excited as I am. All right, so let's jointly open the fifth notebook here. So 05, BERT Feature Engineering. And this notebook here, let me zoom in a little bit. We're introducing how to perform this step of converting the review texts. Let's say this is a great item or not a good product. It's a human text into the features that the BERT model is expecting. And I'm going to also do a brief introduction of BERT as a model architecture, so you understand what we need to create here in this step. All right, so let's do this. So let's go through. So again, here's just a bit of a visual that helps to understand. We're going to use the training data set that we have, consisting of the star rating as the label and the supervised fine-tuning and the actual review text. And we're going to use later in the pipeline, again, the SageMaker Processing Job. Again, this is really a kind of a great tool if you need to perform these processing steps, data analysis steps across a large data set. And the result is then, as you can see here, specific input IDs. That's what it's called. And I'm going to explain it here in a sec, for the BERT model, which it takes as the input. And we're also going to split the data. So into the training, validation, and test data sets. All right, so let's step one step back and talk about BERT as a model. So in the NLP space, natural language processing, and this, I think this picture is now so big it doesn't even fit the screen here. There has been a lot of research and new model architectures being released in the last 10 years or so, right? If I think back, I think the BERT to VEC algorithm I think it was introduced in 2013. And then almost every year, you found another publication from research coming out, introducing a new model, introducing a new algorithm, right? Whether it was, let's say, Elmo, GLOV, GBT, or in 2018, BERT. So BERT stands for, hopefully I get it right, the bidirectional encoder representations from transformers. So quite a term. And BERT was specific in a way that it's used an architecture called the transformer architecture that was presented in a research paper, I think a year ago, a year before, so in 2016 or 17. And BERT used that architecture as kind of one of the first models, and also applied a mechanism called the self-attention. So what BERT is able basically is to understand the context of a word, reading from left to right, but also from right to left. So it doesn't only predict, for example, the next word based on what it was reading left to right, but it also simultaneously learns the context from the right to left. And this sounds simple, but this is really what makes BERT a powerful model architecture, this attention mechanism. And BERT has become really, really kind of a hype, a BERT mania in the industry. And you will see a lot of different variants of the BERT model these days. So there's the original BERT architecture. And what you can do with those models, you can pre-train it on a generic text corpus, let's say on Wikipedia or large book collections. And you can use these models, which we're also going to do, a pre-trained model, to then just fine-tune it really to a specific text domain. Let's say here's one model that's shared, which is fine-tuned to classify patterns, right? And patterns just have very specific text. So this is one of the fine-tunings. Or similar, there's a fine-tuned model that is specific to recognize and work with healthcare text. Then it's called the clinical BERT. And there's also adaptations for the language model to specific languages, right? There's actually a BERT variant that is fine-tuned or trained on, I guess, as well, on German language. So this one is called the German BERT. So this one is also then pre-trained, obviously, on that language. One I like always is that's a fun name for the French language. The model is called the Camembert, like the French cheese. And also kind of the Dutch one is funny, that is called Bertje. So Chris always makes the joke, it's similar to my name, Antje with a J-E in the name, which is also, yeah, you see often in the Dutch language. So all of those are really kind of variants from this BERT model adopted to a specific either text domain or a specific language. All right, so let me zoom back in here. Now, to prepare our raw text data to work with that BERT model, we need to create what it's called embeddings. And I've also put in here links, by the way, to the paper. So if you want to read the official publication on BERT to understand how the transformer architecture looks like, feel free to read the paper. It's really, really interesting. Or if you're interested about the self-attention mechanism, how to pay attention to a word, there's this famous paper called Attention is All You Need. And I've also put in a link here, so feel free to give it a read. All right, so for this workshop, what we need to understand is how do we do the feature engineering, right? We do have the raw text now. And to better understand this, I've put in here, let me zoom, put in here an image to show you how those embeddings are created. So let's start bottom up here. Let's start with the raw text, which is, for example, love this movie. And this is called an input sequence here. So we have a single input sequence. And the first step that is happening in preparing the data is that we're tokenizing the data. And this one here is just a very simple example where I tokenize by the words. There's different techniques and different algorithms to tokenize. And what BERT is using here is called the word piece tokenization. And this actually also does split words into stems of the words. So this would most likely end up not in the full word movie, but let's say maybe move and then movie and movies to capture all of the singular, plural, etc. variations of those words. But for simplicity, I've just put in here the simple words. And part of the tokenization is also adding special tokens, for example, the CLS, as you can see here. And this is indicating that we're looking for a classification task, right? We want to classify this input sequence into later on those star rating classes. All right, and once we have these input texts tokenized, what's happening is that we do a lookup. So the BERT model has been pre-trained, right? So it's using a vocabulary of learned tokens. And we're doing a lookup here. So imagine, and by the way, those vectors are a 768 dimensional space. So they have 768 values in that vector. And we're looking up the token that is representing the one we're feeding in. And this will be represented here by this input ID. This ID is pointing to that entry in the vocabulary. And then there is another input mask applied. And the mask really just tells you which token to pay attention. Meaning, if you remember earlier, I mentioned in the visualization that we do have a model hyperparameter called the maximum sequence length, which is the maximum length of this input sequence we're passing to BERT. So, and we said, given this data set, 64 is a good value, right? So what happens if I just pass in now love this movie? This just has, let's include the special token here, 4 tokens. And if we say we use 64, what will happen is that BERT will fill up, basically pad from the 5th token here to 64 with zeros. And the zeros mean there's no actual value, but we kind of, pad this up to the maximum length. And if I pass in a sequence that has more than 64 tokens, it would cut it down to that 64, right? So it would cut it off after the 64th token. So this is only what the input mask, and then the 1 says this is actually a token, and the 0 is, this has just been padded. All right, and then depending on what you're using the BERT model for, there's different tasks in the NLP space, right? We're doing text classification. Another task is question answering. So you ask a question and the model comes up with an answer. And in that case, you would have here a segment ID as well, which is indicating sentence 1 and sentence 2, for example. If we're only doing text classification, this will always be the 0 because it's one input sequence. We don't need to actually recognize whether we have 2 sentences passed in. And then the one that we do last is the position embedding. And this is really the index position of the token. So the first one has the 0, it's always 0 indexed. And then the second one has the 1 as the index here, etc. So 0, 1, 2, 3. And the input for the BERT model is then the element-wise sum of all of those embeddings, right? So it's, again, those numbers here, it's one sequence with the 4 input tokens or the 4 embeddings here, and then in a 768 dimensional space. All right, so this is a little bit on the theory here, how those get constructed. I just need to zoom out a little bit here. And let's go to the code, right? Let's see how this looks like. And here's an example that shows more from a numerical and code perspective, how those input IDs look. So here you can see, again, on 3 samples of the data, input IDs, again, are the IDs in the vocabulary, where to find the token that we feed in. The input mask is 1, if there's actually a token, and then they get padded up with zeros if it's shorter than the 64 that we're passing. And segment IDs for us is always 0 because we don't do this question answering, we do text classification. So we don't need to take care of whether this is a sentence 1, sentence 2, etc. And then the label ID is basically the star rating. And we always do a 0 index. So the star rating of 1 would be the 0 as the label ID. And the star rating of a 5 would be the 4th label ID, as it's a 0-based index. All right. And let's see. So this is the inputs that we have to generate in the feature engineering step. So let's walk through how we do this here to better understand this before we start building the pipeline. So again, you will see here all of the boilerplate code. So we're defining session, bucket, role, region. What we're also pulling in here is the SageMaker client from the Boto 3 SDK, the client to interact with the F3 service. And what we're also going to do here, exciting, we're going to store those prepared features in the feature store. And I'll explain the feature store here in just a bit. So we're also pulling in the client to interact with a feature store. All right, and with that, we can start here. So what I'm going to show you here is just a brief snippet of code, how to create those embeddings. And we're using TensorFlow and Keras, so I'm importing TensorFlow here, and just a couple of libraries, JSON, OS, pandas, CSV. And here you will see the Hugging Face transformer library again. So if you remember again, we're not going to train BERT from scratch. We're going to use a pre-trained model, specifically a variant of BERT that's called DistillBERT. And this one we're pulling in from the Hugging Face open source library. So really, really cool. And the way you do this is you're installing the transformers, and then you can import the model and also the tokenizer used for the model. So again, the first step is tokenizing the raw reviews, the raw text. And I'm creating this tokenizer here, and I'm pulling it literally from the Hugging Face library. So this call here, if you see that it's DistillBERT tokenizer from pre-trained, this call is actually pulling it down from the Hugging Face repository. And we're just specifying which one we need. So here we're using the DistillBERT variant and base uncased. This is just one of the types of the models and tokenizers that are available in that library. All right, and then we're writing our feature engineering code. So for example, here, I'm specifying which one is my review body column. So this one has the actual review text. And then also one column that has a unique ID. So here I'm using the review ID. I'm specifying your star rating as our label column and the label values of 1 to 5. And because we're working here with 0-based indexes, I just have a little helper function here, which is basically mapping here the label values to an index, right? So the star rating of 1 would then be the 0 index, for example. All right, and I'm creating here a couple of actually classes. So I want to create a class for representing input features, and those are basically the BERT feature vectors that we need. So for example, the input IDs that I discussed, the input mask, segment ID, and let's also add the label ID and the review ID. That one is needed for the feature store, so we have a unique identifier. And let's also make store the date and the actual label. And this makes up my input feature then for BERT. Then I do have another class here specified the input, and this is a single training or test input for the sequence classification task. So this is what I'm going to provide as an input, and here I'm definitely going to provide the actual text. I'm going to provide the review ID, the date, and the label. So these are pretty much the inputs. And then as the outcome of this step, I hopefully get here to my BERT vectors. All right, with those classes, then I can define the actual function. So here, let's say I do this function convert input. I'm passing in the actual input. And here you can see that I'm also specifying now this maximum sequence length, which I was talking about, which is one of those model parameters, the hyperparameter, which is needed in this step. And again, this one just makes sure that all of the input sequences sent to the model have the same length, right? In our case, because 80% of the reviews have 64 words or less, we just chose that value because it works well with the data set. If you're working with another data set, you might just explore your data and adjust it to whatever makes sense. So again, this is the value passed in, and we have to carry that through the same setting in the feature engineering as well as later when we fine-tune the model. So it's actually a pretty important hyperparameter. All right. And then here in this convert input function, we're creating the tokens. So here we're simply use this tokenizer, which we pulled in, and call the tokenize function. Couldn't get any easier than that. And providing the input here, the text from that input sample. So this is the raw text. And in this example here, because the tokenizer doesn't necessarily show the separator special tokens, so we're inserting this here just for visualization. And also appending here this separating, which is used after the sequence in case we have a second sentence. We're just finishing our sequence with this. And those are special tokens that we just add here because we want to show you how this actually looks. All right. And the next step then is to encode. So this encode and encode plus function will actually create those embeddings. So again, we can use the tokenizer encode plus function to receive those embeddings. And we're passing in the text again. We're setting here the setting that we're padding up to the 64, to the max sequence, to true. And we're passing the actual length that we defined. And we're also saying that we truncate everything that's coming in with more review length up down to the 64 value. And this is creating those embeddings. And then you can literally, from that resulting dictionary here, look for the input IDs, look for the attention mask, it's called, which is then the input mask. And it doesn't generate the segment IDs because the still BERT for classification doesn't need it. So we're just manually creating to show you how.
Muted.
We're creating the label ID. Again, we're using here this function that we use that converts the actual label, let's say starting 5, to the 0 index. So this would become the index of 4. And then we're putting this and creating
Muted.
defined. So we're converting this into an official input feature, passing in the input IDs, mask, segment IDs, label ID, the review ID, the date, and the label. And we're printing, so you can see how this looks here. All right. And then here, what we're also doing is we're using TensorFlow as the framework of choice in this example. So another optimization in TensorFlow is that you can convert your training samples to TF records. And it's just an optimized format for working with TensorFlow. So we're doing this here. So we're using the TensorFlow built-in functions to write data out as a TF record file. And this is happening here. I'm not going into each line of code, but this is basically converting the raw data files with those created embeddings then into TF record files. So this is going to be our training data. All right, so let's see. Here's again a little bit of explanation. Let's see how we can run this now, right? So let's do this. So far, we defined the classes and we defined the functions. So let's actually run this. And this notebook here, if you're wondering, we're running it on just 3 samples in the notebook itself to discuss the concept, right? And this would be if you start building your model, you start prototyping, right? You want to make sure when you're building up that code that it's functionally working and it's working correctly, right? So you would just start prototyping and you want to iterate fast. And this is what we're showing here. We're then taking this code and running it at scale on the large data that is sitting in S3 when we're building here the pipeline in the second next notebook. Okay, so this one is executing it very simple in the notebook itself, just to show you from a conceptual point how those steps work. What we're doing is we're also ingesting those generated features in the feature store. So think of a feature store really as kind of a central repository where you can store and then share those created features, let's say with colleagues, coworkers, team members. Because depending on your work here, you're spending a lot of effort in creating those, right? And there's a good chance that other team members, co-workers, maybe in different departments, have a similar task at hand, and they also need to create maybe those features, right? From given data sets, maybe from your company, etc. So a feature store can help you to check in those features to a central data store and share it with other teams, and other teams can get those features out of this feature store and reuse them in their projects. And again, feature store that AWS
Unmuted.
at the last reInvent conference. So there is a managed SageMaker Feature Store that you can literally use to store and then share those features. All right, so let's see how we can do this. So to store the features, we need a record identifier, and in our case, we're using the review ID, and we need a timestamp. So this is what we're going to do here. We're just setting a timestamp, and then we need sample data. And again, this is just a conceptual proof that our code is working. So we're literally just doing 3 samples here to show that everything works as expected. So I have input, my 5-star rating. I have a review identifier here and a review text, right? So I'm just putting in a text here. And in this case, I'm pulling it into a data frame. And then I'm creating the input object consisting of the label, the text, the review ID, and the date. And I can check that everything is set here. So for example, I can print the date and I can see the date stamp here. All right, so moving forward, here, for example, I saved the TF record files as well, if you're interested. Let's see how the feature store works. So first of all, what I need to do is to create a feature group. And think of a feature group as just logically grouping those features together. So in our case, we could call it, it's, for example, this still BERT embedding with hyperparameter model settings, max sequence length 64. So you want to get a little bit more descriptive here to differentiate and name your different feature groups. In this case, as we're only going to have one here in this workshop, I called it reviews feature group and then just the timestamp. But obviously, you can encode much more meaningful names here in those groups. And I think we're doing it when we're doing it in the pipeline step, actually. So, and then you can import here just from the SageMaker Feature Store definitions, those types, the feature definition and the type definition. And here we're just giving it kind of, again, the metadata information, right? So how does the individual features you're checking into this group look like? And in our case, it's the known suspects, so the input IDs, masks, segment IDs, etc. And we're just specifying here, again, similar to the table metadata before. This one is type string, this one is maybe type integer, etc. So we need to kind of define the types and the names for the individual features. All right, and with that, we do have this logical grouping in place. We know how the structure looks like for the features. And we can then create this feature group here officially as an object using this call from the SageMaker Feature Store. And here we can see the group is built. And again, we need a unique identifier. So here we're using the review ID, and we're using also the timestamp here, the date that we created. And there's two ways to create the feature stores. There is an offline feature store, and this one is really used for, let's say, training when you have longer running jobs where you can check out the features stored in this offline store. And in contrast, you can also check in those features into an online store. And the online store is used, for example, if you need to call those features during the model prediction purpose, right? So let's say the review text comes in, and you do a lookup if those texts, the embeddings are already been, pre-calculated, and you can check them out from the feature store, for example, and then pass to your model. So you're saving this processing step in the prediction pipeline, for example. So again, both are available, so you can check them in offline. And the offline feature store is basically backed up by S3. All right, so with that, we have everything in place. So we create the feature group. Here you can see we're pointing it to the S3 bucket. This is the offline feature store where those will be managed for you. And then we're passing the record identifier and the time role. And we can also, here you can see, enable online feature store by setting this argument here to true. All right, and this creates the feature store, the group, and everything. And we can describe the feature group, and here you can see it picked up the definitions and everything that we need. So it looks good. It takes a little bit here for the group to be created. So here we're just checking and waiting until the feature store is online. This just takes a few seconds. And then we can create those inputs, right? So let's say we use the maximum sequence length 64, and we're creating records by calling the function that we specified, transform inputs to TF record. And this takes the inputs. We're specifying where to store the output file, and again, the maximum sequence length. And here you can now see those three input sentences or like reviews that we generated. Let's just say here, the first sentence comes down to be 37 tokens. And you can actually see here how those word piece tokenization works. So some words will have this # sign before, and this is like how stemming works, right? So the tokenization is not always creating the full word as a token, but it stems down to, in this case, the ER. And this is also, I don't know if we have questions here in the Slack, how the model handles out of vocabulary tokens, right? What happens if you pass a word that the model has not been learned yet? And what BERT will do is, in this tokenization process, it will go down smaller and smaller until it finds a token it has learned, right? The ER is most likely a combination that it picked up from somewhere. So this token will be in the dictionary, in the vocabulary. So this is a nice way to also avoid running into this out of vocabulary situation, because as you're going smaller and smaller here to the stem of the word, you will have most likely a match. All right, so the input sequence here is 37 tokens, including here those special tokens that we added. And again, we set maximum sequence length to 64. So what will happen, and here you can see this nicely, you have the input IDs, again, reflecting the ID where to find this token in the vocabulary. And everything past the 37 will get padded with the zeros to match 64 input IDs now. And the mask, the 1 reflects this is an actual value, and the 0 reflects this was just padding happening. And then in this case, here segment IDs we wouldn't even need, but just for the completion, again, those are only needed if you do question answering tasks, or where you basically pass into sentences. For text classification, this is not needed. Hence, we're just setting this here to the zeros. And then label ID, here again, this was a 5-star rating, so the ID would be 4. zero-based index. We do have the review ID and the date, and similar with the other examples. And this is basically what we're ingesting now also into the feature store, right? Because we just spend so much time creating those, so we want to share them with potentially coworkers that need the same features. And I'll show you how you can ingest those. So again, here we're just saying, let's assume we have those here in a data frame. And here you can see the input IDs, input masks, segment IDs, etc. We're also adding, for example, here a column that says the split type. So this would indicate, for example, this is the training split of the data. So when you're training the model, you can check them out and say, I want to check out those features from the training split. And then if you're doing the validation of the model, you could, for example, get features from another split, which is the validation, or later on, maybe the test split. And this is really just, you have the freedom to construct those as you like. We just added this here because I think it makes sense in this case, where you want to maybe classify those features as well, training, validation, test splits. All right, a little bit of casting here just to match the generic object, which is coming back from the pandas data frame to be, in this case, we need string objects. And then you can call the feature group ingest, passing in here the data frame, and this will ingest now those features into the feature store. And you can also retrieve them, obviously. So how you can do this is using this feature store client, for example, that I imported in the beginning, and you can call the get record, and you're specifying the feature group name and the individual identifier. And here again, I use this review ID, which is used as the identifier to retrieve this specific feature. All right, so this was a little bit more detail on how to do the feature engineering for our BERT model. And again, this one ran completely in the notebook because we just used 3 sample lines of samples to show you from a conceptual perspective how this works. And this is probably how you would start prototyping, right? You don't want to actually wait maybe half an hour to do feature engineering on the complete data set while you're still in the prototyping phase and want to quickly iterate, change code, develop the code, etc. We will take this code then, as I said, in the pipeline to then scale it out and really use the SageMaker capabilities like processing job again to run this at scale across the data set in S3. But this first to give you all an understanding how this works. All right, so this was the feature engineering. And next up is the model training. And again, 06, the next notebook, if you want to open that, is also from a conceptual perspective showing you how to do the fine tuning. And then we're actually going to do it in just the next notebook then in 7 when we're building the pipeline. And not sure, let me see if Chris already mentioned this in the Slack channel. What you could do now, and what I would like to ask you is, if you jump to 07 right now, and make sure you're running 7, because the pipeline will actually take 30, 40 minutes to execute. So we want to make sure that one is already running when we're getting to it, and then hopefully finishing soon. So if you don't mind, open 07, SageMaker Pipelines, and do a kernel restart if you haven't done so. If you've already run that, keep it. But if you haven't done so, do a restart kernel and run all cells and make sure 7 starts executing. So I started that before, and just let me verify here that has hopefully executed. Looks good. All right, so run 7 and keep the notebook open. It will run for 30 minutes. So we just want to make sure that that one is in run. All right, checking in briefly here to see with Chris if there's anything, big questions we need to address.
I think we're good. And just a reminder, there's about 1 hour left. We're going to keep the accounts up for 1 hour afterward. If you still haven't received your account, ping me or Ancha, or just post it right to the main channel, and we'll get you the link. I could take over at this point, Ancha. we're on 06, right?
Okay, you're ready?
Yeah.
Sounds good, yeah. So again, make sure everyone, I see a question how to run 7. So open up the 07 notebook, and I just checked if my pipeline ran. And do kernel, reset kernel, and run all cells. And this will run through the whole notebook while you keep it open, and we can follow along the 6 first to introduce you how to do the fine tuning. But make sure you're starting 7 and do reset kernel and run all cells. Just do it once. If you've executed, if you jumped ahead maybe and already executed the notebook, it's fine. Just make sure you started it and completed it once. Yeah, and we do have 1 hour left, Chris, so you probably want to be brief on the 6th so we can have time for the pipeline notebook.
Okay. And yeah, there's still a few people asking for the accounts. So actually, let me just do this here. Or let's see. Yeah, a couple people asking about the accounts. By the way, the link to the accounts here, I'll just post it right here. It's the same link actually that we did earlier. We were just throttling there. So, okay, let me take over as presenter. I got the right screen. Okay, can you see okay? Hopefully, yeah, Ansha, can you see?
Yes,
All
yes,
right.
I can see the notebook, yeah.
So you made it up to 05. Okay, so let's take it from here. Oh, and then, yeah, for those of you that need to drop off, we do have the recording. So that will be posted. Let's see, here's all the links for everything. And there's a link to the book, a link to the GitHub repo that powers all this. All of these exact same samples are in this GitHub repo and YouTube channel. Okay, so Ansha walked us through how to do the feature engineering, and we're going to eventually do all of these steps within Create SageMaker Pipeline. We're just trying to fill in what's actually happening within this pipeline. What we realized was if we start with the pipeline, it's all kind of like behind the scenes and can't really tell what's going on. So we're sort of incrementally building up to what's happening here. So now that we've got TF records, which are binary, packed, super efficient, they're very well known by TensorFlow. We actually chose TensorFlow specifically for this reason because of TF record. PyTorch typically just uses CSVs, and which is not a problem typically, but yes, I've personally done much more TensorFlow in my career, and am very familiar with the TF record format. And so TF record is protocol buffers. It's not human readable. Yes, Ansha showed you what that looked like. Now we're actually going to take those TF records and we're going to fine tune BERT. And so BERT actually comes pre-trained. BERT has been pre-trained on millions and millions of documents, like Google Books Corpus, Wikipedia. There's versions of it trained on like Reddit. Yes, all kinds of different versions, as Ansha showed with the BERT Mania. But now we are going to reuse that knowledge. Some people call this transfer learning. This is actually technically, in this case, called fine tuning. There's some subtle differences between like transfer learning and fine tuning. But what we are doing here is reusing all of the knowledge, and specifically language knowledge, right? Like this natural language understanding. And we are now going to run through our specific data set, right? Which is a public data set of these Amazon customer reviews. And we're going to fine tune it to learn our specific data. So BERT knows quite a lot about language, but it doesn't know much about our classifications, right? So our star rating 1 through 5. And so that's the actual fine tuning. And so technically, when BERT was pre-trained, that was done in an unsupervised manner. And so BERT didn't know about classification or about question and answer. all BERT knew about is there's this big blob of text or blobs of text, and BERT was trying to make sense out of it. Now we are going to narrow in and specifically fine tune for a specific task, which in our case is text classification. And so text classification doesn't always have to be, some form of sentiment or star rating. Text classification could be, I'm trying to figure out what category this particular news article is, or something like that. So here's just kind of more sort of visual flows here. Pre-training, we have reused a pre-trained model, and yeah, so Ancha showed you some of those different variants for language or for different domains like healthcare, for like biology, for patents, and some of the larger companies like LinkedIn, of course, folks right like us. Yeah, so like Amazon. There's lots of corporate examples where they have actually pre-trained BERT specific to their domain, right? So for like LinkedIn, for example, they have pre-trained a variant of BERT that makes sense for job listings, job postings, resumes, things like that. And then they fine tune from that pre-trained. So the version of the pre-trained model that we are using is quite generic, but that tends to work out okay. Now, I saw some of you on Slack ask, if you're seeing poor accuracy, that's because we only have time to train for about 30 minutes here. And we are using a smaller subset. If you take a look at the book, we actually trained for, I believe, about 9 hours, but really after about 2 hours, we hit, I think, about 98% accuracy. In some cases, we were overfitting, right? The validation accuracy was a little bit below that, but it really shows you how powerful BERT can be and like how much knowledge BERT has about language. So we are going to use the still BERT, like Ancha said. This is a much lighter weight, has many less parameters, but still maintains about 97% of the overall accuracy. This was actually created by the folks who created Transformers, which is Hugging Face. It's a pretty popular library. I think it has about 35,000 stars on GitHub. And so our job is to unpack that TF record and pull it into TensorFlow. Now, so TensorFlow knows about TF records natively and can unpack these things, but we have to kind of hint what we put into this TF record so that TensorFlow knows how to unpack it. So that's really what this decode boilerplate code here is. We're going to shuffle our data set. This is usually a good idea. If you continue to show the model the data in the same order, for example, each time, the model might actually learn something about that order, and that's not what you want typically. Now, if you're doing time series, yeah, that's certainly what you want, but we are not doing time series data today. We are using just regular flat classification data. So we definitely do want to shuffle. Yeah, that's always pretty much a standard practice these days. We also split into train, validation, and test. And so I believe Ancha talked about this a little bit maybe for the feature store, but we do want 3 separate data sets. We want to train with our train split. We want to then validate the hyperparameters that we chose. Today we are not talking about hyperparameter tuning. Chapter 8, I think it is like pretty much all about hyperparameter tuning. So check that out. And there are samples within the book folder here that have all of the like hyperparameter tuning. But like typically we are going to use 3 splits. So we train with 1 split, we then validate and check our accuracy, which is typically called validation accuracy, with those hyperparameters. And then there's one final holdout, which is called test split, which we then use to further test. And what we're trying to do is to not leak information. So when we train, the training set does not see the data that has been held out for validation. And then furthermore, when we validate, that the test data has not been seen. So that's why we see sort of concentric ring, if you will, 3 different layers. So yeah, I mentioned hyperparameters. We are going to just manually choose hyperparameters for today. Yeah, hyperparameter tuning is pretty well documented, pretty common knowledge, pretty like Googleable these days, and of course yeah, in the chapter 8 from our book. And so here I'm just picking hyperparameters. So these are called hyperparameters, by the way, because when we train a model or fine tune a model, we are actually learning parameters. And so the way that we learn those parameters is done, so that's configured through something called hyperparameters. So it's a fancy name for just more sets of configuration. And so Anta showed earlier, I believe it was in 03, that max sequence length. So this is a super important variable that, hyperparameter that needs to be passed in to BERT during both feature engineering and during fine tuning. And so I didn't run the sample, so I don't have the image up, I don't think, but I think it was 80th percentile is less than 64. And so max sequence length is just one of these hyperparameters that BERT needs. BERT needs to build these buffers. And if we choose larger numbers, it's just going to be larger buffers. And so we want to go as small as we can, but still capture, right, like most of our data, or 70th percentile. In like our case, this is actually 80th percentile. Of the specific review text is less than 64 words, or technically 64 tokens, as Anta showed you, where multiple tokens can define a single word. Okay, so now we're defining our classes. Here we have 5 classes, and we are giving it ID to label, label to ID. These are, so this is where we have 0 index versus 1 index. So in the sort of human world, we have the star rating 1 through 5. In the software world, we have 0 index, so it's 0 through 4. So that's where that mapping's happening right there. And here's just some fun Keras code. Funny enough, this actually ends up being sort of the least interesting part of all this. This is now so simple to do, especially with this transformers library that we are using. It's just a couple lines of code to pull in 66 million parameters and then set it up to train on our specific data set. So a few years ago, we'd be hacking this out and trying this over and over and trying to figure out the best parameters here. And like these days, I just make one line of code call, and that actually pulls down this model, and I could just do a nice thin layer on top of this huge network that has been pre-trained for me. So this is a simple classification layer, or like relatively simple. We see softmax here. We're doing multi-class. And let's see. So this downloaded that pre-trained model was about 360 megabytes. I think the full BERT is, I think, maybe 500 megabytes, 600 megabytes, something, maybe even larger. Just kind of skip these warnings. These are just Keras complaining about certain things. Here's the 66 million parameters. Oh, and so here's our loss function here. So categorical cross entropy. Here's our accuracy metric, which is what we are trying to optimize. And then here is the numerical optimizer that we have chosen to use, which is called ADAM, which is a form of stochastic gradient descent. And whenever doing stochastic gradient descent, you almost always see learning rate. That's sort of the step that we're taking as we are following and calculating these gradients. Here we are pulling them all in, telling Keras to use all of these 3 building blocks. Let's dump out the summary. So here's inputs. So this is one layer that has 66 million parameters. So back in the old days, we had to actually build this ourselves. Now it's just one simple API call. Here's our classification layer. So this is the actual fine tuning right here. And then finally giving us and so I kind of glossed over this, but there's this flag that's called freeze. And I could choose to actually freeze the base BERT layer. So in this case, this is distill BERT. And when I'm fine tuning, I'm just going to skip all those layers and not change any of those parameters and just change the thin classification layer that I've put on top. Now that's going to train a lot faster. It's going to take less memory because we don't need as many parameters that are changing. And there's some systems optimizations we can make if we're not actually making changes to these floats. But we can also choose to unfreeze, which will give us slightly better accuracy. We do freeze in the notebook because we do want to keep memory down, but we do unfreeze when we actually do the full pipeline and we have a cluster. And so if we unfreeze, we are actually able to now modify these 66 million parameters when we are fine-tuning. And so it just sort of gives us a few more degrees of freedom to learn this, fairly complex data set of natural language. But again, we'll see here that we are really, for like this case, we are not training most of those 66 million. When we do flip this over to the cluster, which is 07, we do actually unfreeze that, I believe. If we wanted to, we could actually run TensorBoard here through the notebook, but let's skip over that for now. And this is where all the things come together. So here we are actually fitting our model. So this is calling Keras.fit. We pass it the training data set. We pass it the validation data set. And so train, validate, it's going to go back and forth and do this. I think we only do this for a few steps, so our training accuracy shows up as 0, so that's not very good. But we will get, our training accuracy is actually 37.5, but our validation accuracy is not very good. So we, in 07, we do get better accuracy, still not state of the art, just because we are only training for about 30 minutes here. And then this is using that third holdout. So train, validate, then we still have this third holdout, like I said, concentric ring, if you will, or splits of data that can't see each other. And test is then used to give us a test accuracy, which is actually coming in at 50%, which seems kind of odd, or just very lucky. Here we are saving the model. Yeah, so now I'm showing you sort of piece by piece through the notebook, but when we go to 07, which hopefully you have already started running, all of this will be done on the cluster. We're saving the TensorFlow model. This is a fancy trick here that if you've spent any time doing TensorFlow and trying to actually deploy TensorFlow, you've probably stumbled upon this. Save model CLI. This actually dumps out what the inputs to the model are. And so here we have input IDs and then input mask. And so these input IDs are those actual token IDs, right, that Ansha showed. And then we have the input mask, which is the ones and zeros as to which tokens to actually pay attention to, which is typically the first, 64, or if the review comes in less than 64, it will get padded up to 64. If that review is actually larger than 64, it will get truncated. And so that's why you have to really pay attention to that max sequence length. Now there's been some improvements to BERT, or some more modern versions. One's called, I think it's called Big Bird or Big BERT, something like that, that can handle larger. Right now, the BERT only goes up to 512 tokens. If you do need to go beyond 512, you can certainly use bigger versions of BERT. They will take up more memory. Oftentimes, we see people taking the first sentence of a paragraph and the very last sentence of a paragraph, because typically those two do capture most of the meaning. So that's one way to kind of get around it. That's a feature engineering trick that you would have to try and then load your feature store with those different versions and see what works. Here, I'm just showing how we can load the model back in and make a quick prediction. And yeah, this is a pretty poor model because this trained for like literally seconds, but just showing you how the plumbing actually works and how all this comes together. All right. Yeah, Ansha, should I move on to pipeline?
Yeah, I think that sounds good.
Okay. Let's see if it actually ran here. Looks like we got one. Oh, and I started mine a little bit later, so it's still probably running here, but let me walk through it, and by the time we get there, it should be done. Yeah, so head on over to 07, create SageMaker pipeline. Hopefully you have already started that. These last few go pretty quickly, by the way. So once this like 07 runs, I think 08 runs for just a few minutes, and then 09 and 10, and then we will ultimately then deploy the model. And like, don't worry about cleanup. We are going to tear all of these accounts down. If you are still using your own account, you'll have to, you will want to run that. It's just gonna, I think, tear down some of the SageMaker endpoints that are long running after we do the deployment step. Okay, SageMaker pipelines. So pipeline's pretty common term these days. Workflow pipeline, sometimes used like synonymously. If you're familiar with something like Airflow or even Kubeflow, so SageMaker pipeline is very similar. You build up a directed acyclic graph, so a DAG of steps and then conditions, and when those conditions are met, steps can then continue on. You can chain steps together, of course. You can have failures for if a step fails, it can retry, yes, all that stuff. And you can actually cache steps. So caching certainly helps out. So let's say you want to rerun the same pipeline with the same TF records. You don't want to necessarily regenerate those same TF records because that took some time. That took 10 minutes or something. And so you want to turn on step caching, and just as long as that data has not changed in S3, yes, let's say we only get like daily updates, for example, of these reviews. We get like daily dumps from the review team into like an S3 bucket. I'm just making this up. I actually don't know how that works. We would not have to rerun that whole feature engineering step because we can just go into the feature store, grab those TF records, and then run just the actual modeling, like fine tuning. Okay, so pipelines consist of processing job steps, which we have seen a little bit of, I believe, which is really generic. Processing jobs are, fairly generic. You can put in Python code, Java code, whatever you need. You have inputs. You have super fast access to S3. You can then pull, and once the processing is done, that's typically where feature engineering is done, you then pipe the output of the feature engineering into the actual input for the training job. So that'll train just like we showed in 06. So 05, the feature engineering is really what's happening in processing jobs. 06 is training jobs. And then when the model is trained, we will check to see what is the actual validation accuracy, or I think it's actually test accuracy. If it's above a certain threshold, so because we have 5 classes, just to start, like we will say 20%, because if a trained model does not have better than random chance, right, then there's no reason to continue, and we wouldn't even bother deploying this into production. We would keep the current version, or just scrap the whole thing and then find some new data and see if we can retrain and get better accuracy. But yes, and I think this one comes in at maybe, I think after 30 minutes, maybe 30%, 40% accurate. So we will check that. If it does actually exceed 20%, we will then conditionally deploy and register this model and deploy, which then jumps ahead to the 11 down there. And we could also do batch transformations. I think today we are just going to deploy endpoints. All right, let me take another look here, see if this thing is still going. Oh, okay, so this actually did finish. Yeah, okay, yeah, here it is. So this must have just finished. So if you go over here, and that's what the next step here is, it's showing you how to take a look at this. Go to this little triangle thing. Yeah, I've never quite understood what that is, but someone within the Studio UI team knows. and double click in here, and I can actually click on each of these individual steps and see, here's my processing job. Those are the 3 splits. So this started with those Amazon reviews that were in TSV format for this particular example, and converted them into TF records. And if I zoomed out, you could see the full URL has, I think TF record is the extension. Let's click on over to train. And here we see all of the results. So here, validation accuracy, 35%, not very good, which is why I think someone posted that they were trying to make changes to the predictions and seeing poor predictions. And this is why. Yes, if you train for another hour, let's say, you would actually get much better results. Yes, like I said, for the book, we got like 98% or something crazy. So here we could see the validation accuracy. There's training accuracy. Let's hop on over to look at the test accuracy. And I don't think this view actually shows it. We could see it in the, let's see, if I look in the logs, I think I could see it. We'll see it here in a bit because we're actually going to evaluate it and show you how that's done. Actually, I think in the notebook, we actually show it. Yeah, so let's assume that this does return something greater than 20%, which is the threshold. So let me click on accuracy condition. This actually did, yeah, so this like ended up being true. So then it goes to, let's see, zoom this thing over here. So true does 2 things in parallel. So it's going to register the model, which means something in the SageMaker world. When you like register the model, you are telling SageMaker where the actual trained model is, where that TensorFlow model is, and we are actually going to then create the model to then prepare to deploy it. And so let's jump back to the notebook. Let's see. Okay, so I still haven't shown this here. So here is what we ended up with. Same thing I was just showing you, slightly grainier version. And this is how you actually construct the DAG itself. And so we only have about 35 minutes, so I'm gonna breeze through this here. But basically, we have to create a DAG. And so this is kind of a horizontal view of it. This is the like vertical view from the actual SageMaker tool itself. But now this is a horizontal view. Processing step, which is feature engineering, which once again is 05. 06 is training. But now these were small data. This is starting to get bigger data because we actually have a cluster, right? And so that's really the whole point of all this. Some of you might be asking, why am I doing all this? I could just do this with like NumPy, pandas, and a Jupyter notebook. And that's certainly true, but there are limits to that, right? There's just physical limits to the amount of data that a single node can process, which is why we have to switch to the cluster, which is the whole purpose of our book. So here, feature engineering training, we then do the evaluation. We check if the accuracy is above that specified threshold, and then we will just do create model and then register model. If it's not above the threshold, we will just end the pipeline. So here's some of the boilerplate. We're showing how to get to Feature Store, how to get to SageMaker. We're going to do all of those steps now. So all of the stuff that like Ancha showed you earlier will now be done as part of a single DAG, or a directed acyclic graph, and using the SageMaker pipelines. So we do have a little bit of boilerplate here because we tend to see people right, like running and then rerunning. People get sort of frustrated that this notebook takes so long. So we have some programmatic safeguards in here, yes, if you will, to prevent that, because otherwise you will run so many jobs that it just doesn't return, or it just gets into a weird state that's very difficult to debug at scale, like we are today. So the first thing that we do is actually create this experiment. And we want to run the pipeline in the context of an experiment because we want to track it and compare it to future runs. And so this is SageMaker speak. Some of this actually has been getting rolled into SageMaker more natively, and specifically pipelines, so that you don't have to deal with this. But this is some of the boilerplate. In some cases, you actually do want to specify your own experiments because maybe it's part of a larger experiment. And so we could pass that in. Here's the placeholders. So now these are the actual parameters. These really end up being hyperparameters. They're called parameters here, just in the context of a pipeline. We have strings, integers, floats, pretty basic stuff. And this is how we will pass in hyperparameters. This is how we'll pass in if we want to freeze, unfreeze, that kind of thing. And so you've seen this before. So this is just doing it as part of the pipeline where we're transforming raw reviews into BERT TF records, TensorFlow TF records. Here we see some of the hyperparameters coming into play. So all of these are specific to some step within our pipeline. So max sequence length is used twice. It's used in both processing, the feature engineering, and training. Whether or not we're going to balance what our train validation test split is. Where's our feature store? Because that's where we will get some of our data for training. And then here's setting up the processing job. So I'm going to skip through this because this is sort of logically, well, this is quite a bit of code to end up with what I had shown you over here, which is the actual graph. So by the way, this is super exciting to do maybe 2 or 3 times, like writing this code. It's just like Airflow. It's just like Kubeflow. It's super fun to do, a few times. And then after that, it's just like, okay, I just need to fill in like my exact values. And then at that point, you start playing with just the specific hyperparameters. Here, I could scale this job up. If I wanted to do 10 nodes, I could just change that to 10 right there. Here's my other hyperparameters. So this is for my numerical optimizer. So I have my learning rate for my gradient descents. I have number of the epochs. So one epoch, by the way, is one complete pass through the data set. And you typically want to do multiple epochs, and you want to shuffle in between because you don't want the model to learn the specific order that data is being presented, or the way it's stored on disk, for example. Here's some other hyperparameters specific to TensorFlow. In some cases, is actually more for GPUs here, and for mixed precision. We can skip those for now, but here's our freeze. If we were going to use checkpointing, which is very useful when we're doing spot instance training and could potentially lose a node in our cluster, the whole book talks about spot as a form of cost savings. Yes, like I said, each chapter has a section about cost savings, and spot instances are a huge part of that, and therefore checkpointing. Today we are not checkpointing because we actually want to make sure that, we're not too worried about costs today because we are actually paying for this, and you do not have to. Here's where so TensorFlow and SageMaker are spitting out logs during training. We can actually capture the print statements from Python code and then convert them into numbers. And so that's what this regex does. This is saying TensorFlow is actually spitting out lost colon. I could actually add my own specific code, or write like my own logs, and have those numbers end up in something like CloudWatch. And then, so this represents validation accuracy, test accuracy, and then these all show up within CloudWatch, which is pretty cool. This is actually one of my favorite sort of subtle parts of SageMaker. And super flexible, kind of shows you that there was some forward thinking here where these different frameworks have different ways of specifying what's happening during training. And so SageMaker gives you the flexibility to tap into whatever you need there. And so most of this actually does come out of the box for free. I throw it in here just to show the flexibility. Now we're going to talk a little bit about Profiler here. So this is one of the newer features of SageMaker, came out, I believe, December of just this past year, so just a few months ago. Profiler is keeping track of what's going on during training, and it's tapping in every 500 milliseconds, every second, every 10 milliseconds, whatever you specify, And it's going to capture system metrics. It's going to then, it will then make recommendations. So this is one of the cooler things here, where it will recommend how we can potentially change our job. And so I'm going to click on quick start. Let's see, there's a directory called generated profiler report. And so this is super slick. So this has nice pie charts. Yes, everyone loves pie charts. Talking about system usage metrics, framework specific, how much time was spent doing training during like evaluation. And then this is my favorite thing here. So this is actually telling me that I think this is telling me I should try a different distributed strategy. Actually had it disabled, so not even using it. In this case, it's telling me my batch size is too small and consider running this on a smaller instance. So this is pretty rare when you see a cloud provider telling you to run it on a smaller instance, or so you would think. And yeah, so that's why, yes, I always point that out, because it's sort of us telling you when you are actually using too much hardware and should actually scale it back or increase the batch size to better utilize those resources. And here we aren't actually using GPUs here, but we do actually make suggestions about it. And so the trick here, by the way, I'm sure people might be asking, but there's this trust HTML and then distrust. So you have to be careful that if you don't trust, these images don't show up, the pie charts. If you trust it and then maybe hit the refresh, you'll see the pie chart there. So that's under generated profiler report. Let me go back to the notebook here just to make sure that we get through this. Here's where we specify our training script. So training script is essentially a more of a server-side version of what we were doing in our notebook. So in our 06 notebook, pardon the scroll here, let me get to the interesting stuff. If I put this side by side, so there's my Python script. Let me make this a little, so I should be able to search for this over here and find a similar reference. And so there it's from pre-trained. I should be able to search for bidirectional. Let's see. So I used the notebook to sort of ad hoc figure out what I want to do. And then I move that code into this more server-side script, Python script that can do things in parallel and has much more hardware, can like do things distributed, can like utilize all of the CPUs and GPUs. But at the end of the day, this is still just TensorFlow Keras code, or PyTorch code if you were doing that. Here we are actually handling checkpointing. And so some of this code looks a little messy, and it tends to get messy when it's more server side because there are more files coming in parallel. We're dealing with much bigger data. But here's our loss metric, our loss function, our the like accuracy metric that we're trying to optimize. And I think the gradient descent, where's the actual optimizer, is here. Optimizer is defined up here, and that's where we're specifying learning rates and all that stuff. Okay, so that's where all of that comes together. Here's all those hyperparameters. Now keep in mind, these are actually expressed, and these are simply placeholders because this is just one piece of our whole pipeline here, right? That's just that single training step. And so I'm just saying at some point, I'm going to actually provide you with a value for learning rates. And right now, just make it a placeholder. But this looks very similar to the other code if we were actually specifying the physical values here. And that, of course, is by design, so that like we could use the same code inside of a pipeline, outside of a pipeline. Here's where we turn on step caching. It's not really going to help us much on the first run, but there it is. Subsequent runs will pick that up. And here is where we're setting up. Oh, and so this is actually now snapping in that same estimator into the pipeline. And then, so once again, these are actually placeholders pointing to previous steps within our directed acyclic graph. And so training actually depended on the previous processing. Now we're actually going to evaluate the model, which is itself another processing step. And I'm kind of skipping over some of the code here, by the way. Some of you might be asking, where is all this code coming from? There's some Python scripts here that we are not going to have time to go into, but you can certainly check them out. This code's all out there. And here, we're just literally wiring up everything. So this is going to take a look at the output of the model. And let's see. Oh yeah, this is always that sort of weird place where I have to define the leaves of a tree before I can define the parent. So I'm setting up this register and that create, and I'm then going to attach it to this condition, which will have that threshold. So I'm just going to skip through this because you could see all the code here, but at the end of the day, oh yeah, so actually this should be 20%. But yeah, it looks like I set it super low when I was putting this together. So min accuracy, if the model's accuracy is not above 1%, which is really low, this should be higher. And I could actually change this value so that the next time I train, or I'll train once, I'll get 20% accuracy, or yeah, let's say I get 37% accuracy. I will then update this value so that the next time I run, I'm not going to push that model into staging or production unless it's better than the previous run of 37%. And so this is just, yes, right. So all of these graph, yes, Airflow, Kubeflow, they all have some way to specify steps and then dependencies. And so that's how SageMaker Pipelines does it. And then now, yes, everything comes together where we create the pipeline with all of the parameters possible. We give it all the steps. This condition step actually contains those other two steps, create and register. Here we start the pipeline. You know, again, just some boilerplate here to prevent chaos and what is commonly called rage clicking, where you're just hitting, you know, restart, run 1,000 times because it is taking too long. And so all of this comes together. We will actually deploy it as well too. And this all finished. Let's see, we keep going here. And I think, oh, and then this is the other cool thing that was released in December is this lineage tracking. So this actually tells me what was the script that was used. So this is each step, by the way. This is the processing job, shows me all the inputs, all the outputs, shows that the training job, and this actually tells me which, so which Docker image was used, which script was used, where is the data coming from, so which bucket in like S3 is this coming from, and then all of this comes out. This is the evaluation step, so there's the evaluate model metrics, which is this script right here. It was a Scikit-Learn like Docker image. And then all of this comes together, and this says it is pending manual approval, which we will do programmatically in another step here. Okay, so profiler report, I jumped ahead and showed you already. You could also, by the way, view the profiler if you follow these steps in Studio, but I'm going to skip that for now. And okay. Yeah, Ansha, have you run the evaluate? I actually didn't run that for some reason.
I did. I can flip over if you like.
Okay. Yeah, do you want to finish it off?
Yeah, let me, just was answering questions here. So let me flip over here. And I'm going to grab the screen share from here. Let me see. I got the right screen here.
Yeah, and quick mention we did give a link for $25 credit, so please grab that. And thank you so much for being patient this morning, and hope you're still deriving some good value out of today.
Perfect. And while I'm jumping over here, Chris, you can maybe have a look at some of the questions I was just typing, and maybe also show people, I think, where they can redeem the credit. All right, so we have roughly 18 minutes left, so thanks for hanging in here. And I do have here the last few notebooks. They're pretty fast, so if you like, and they can run in parallel. If your pipeline, when 07 has finished, you can actually start running 8, 9, 10, and 11. They're pretty much running independently from each other, so you can parallelize those. And I'll show you what's happening in each of those. So after the pipeline, what we're doing in 08, if you open this notebook, is really just pulling down the evaluation. And I see we have a typo here. There's an A missing. We're examining the evaluation metrics. So just real quick, this is a short one, setting up the code here. We're retrieving the pipeline, which we just ran. And we're listing again our pipeline execution steps. I saw a few of you hit a key error before that said something wasn't in there. This is basically kind of the eventual consistency problem that, especially if you do a cell run all, that sometimes those keys are not set yet because the run all is just firing up those cells too quickly. If you see anything like that, and I think I texted all the folks that were hit by that, you can just particularly wait a minute and then rerun that cell. Here, the pipeline is completed, so everything is filled, and we're just checking it's completed. And we're listing the individual steps here again, so we can see all of the pipeline steps. The interesting part here is, if I scroll a little bit further down, is that we're particularly looking for the evaluate model step. And if you remember, we had a little script there that was calculating the accuracy, and you could adapt this to any use case, right? In some cases, you might want to calculate different metrics, maybe F1 scores, other things. In our case, we did the accuracy. And so we're pulling this step, and the output was the evaluation JSON file, right? This was the output that the code of the step executed, generated. And so we're pulling down here, we're reading that JSON file, and we're looking into this, and we can see here the metrics accuracy. In this case, is not too high. It's 0.25, so 25%. But again, we kind of forced it to just train for 20-ish minutes. You can bump this up to much higher accuracy, to 90% higher, if you give enough data and you let it train for a few hours, which we just cut down so we have a chance to see the pipeline complete in this workshop. So in this case, this is the accuracy we get. And we also plotted the confusion metrics as part of the step. So we can also pull down the PNG here, and we can show it, and here you can see the confusion metrics, pretty much representing the 25%, I guess. And yeah, so this is checking on the outputs of the model. The notebook also downloads and analyzes the model. So here we're looking for the train step, and we're describing the training job, and we're copying the model. So here in this step, you can see the F3 model artifacts. This is where the training job will store the model. So we're pulling it down here. And then you can untar, for example, this model.tar file, have a look. And this should look pretty familiar. This is what we generated during the training. So we're saving the TensorFlow model, and we've also saved the transformer model. And then you can pretty much do whatever you want to do. You can take the model, run away with it. You can use here, for example, the TensorFlow CLI tool to peek into this, and you can see the signatures of the model. And one more thing we're showing in here is actually to list all of the artifacts. Someone asked, like in the Slack channel, how does SageMaker pipelines compare to step functions, right? And if you're familiar with the AWS step functions, that's kind of more a generic workflow managed service where you can orchestrate a lot of different services, not only SageMaker and the individual model training steps. So Step Functions released the data science SDK, I think it was 1.5 years ago, that also integrates with SageMaker. And now with SageMaker Pipelines, the difference here, I would say, is really that SageMaker Pipelines is much more integrated, obviously, given the nature, into this SageMaker portfolio of functionalities. Whereas, the power of Step Functions is it can orchestrate much more across the board from AWS services. One thing that is integrated with SageMaker Pipelines is here the lineage tracking, for example. And this is what I'm showing here. So as it's tightly integrated and part of the SageMaker family, pipelines also list here these artifacts. So you can check here, and there's a function called a lineage table visualizer, and it's really just a very simple table. But when you're running this pipeline, it keeps track of all of the inputs and outputs of that step and what contributed to and what got produced. So it's really, really nice to keep track of everything. So you can see here the processing step. We have the Python file, the data set, the actual container image that was used, and they contributed to that artifact. And the output that got produced here, in this case for the processing, was the training data and the splits. And similarly, if you look at the training step, you have the listing, the input training data contributed, similar to the input image used for the TensorFlow training step. And then produced is the model artifact, here the model tar file. So this really lists all of the inputs and outputs and the relationship, the association, whether contributed or produced it, across all of those steps, right? And even here, like when we're creating this model and we're approving it for deployment, it even captures here the type approval that contributed to the actual model later. So really, really cool to keep track of all of the artifacts, and also, integrations, for example, into the SageMaker experiments to keep track of the different steps. All right, so this is theory 8, really kind of just checking on the model, the evaluation metrics, etc. 9 and 10, I'll keep brief. Again, here we're using SageMaker Clarify. If you remember, we used it early on to check the data for any statistical bias and class imbalances in the data set. You can also use the tool to run the same analysis with slightly different metrics once you have trained your model. So just to also, after the model training, see if there's any imbalances, any statistical bias that you want to address before you deploy it, for example, to production. And I'll keep it pretty brief here. It's similar in the way. So you have still the terminology with bias metrics, labels, and the facets that I explained earlier. The only difference here is you're running this analysis now post-training, which means you actually can provide a model. And in this case, we're checking for this statistical bias in the predictions instead of just the data set. And there's a few different metrics in this case that apply to this step. And again, this probably fills a full day worth of workshop and content. But again, I put in here links to follow up and read about the results and specifically what gets calculated. Here's a quick list of all of those metrics. And the code is pretty similar, as I said. So you're specifying where your test data lives. In this case, because we're using a model and our model uses an input format of JSON lines. Here I'm using a JSON lines file with test data. I'm making sure the data is in a 3 bucket. And then I can pretty much use the same steps. Here I'm just looking for my pipeline that it actually succeeded to get the trained model. And then I'm looking here for the name, grabbing this pipeline model that we have now. And then I can specify in a similar way the SageMaker Clarify processor. Again, instance type and instance counts here. I specify the data config. So this is where my test data lives, where to write the report to. And the configuration is just slightly different. I still provide the label, star rating. And I also provide here where to find the features, right? And then the headers of the data set. And in this case, we're not working with CSV. This is an example where we're working, for example, with JSON lines as data. All right, so one thing that comes in addition to the previous step where I introduced Clarify is that here we're actually providing a model configuration, because now we have a trained model. So here I'm passing in the model name, again, the instance type and count, and this will spin up a shadow endpoint. So a model endpoint that is serving predictions, and then Clarify will use the test data, fire it up against the model endpoint, get the prediction results, and then analyze those results to see if there's any difference and imbalance in how those predictions come back. All right, and you can tell it here what's this, how to recognize the return from the model. So in this case, we actually do have a JSON key called predicted label that then contains the prediction result. And you specify, again, the bias configuration here, positive value, still the 5 and 4 in our case, facet name, product category. And here, instead of running the pre-training bias, you can call a function called run post-training bias, giving all of those input configurations we discussed, specifying with methods to calculate, and you run the job, and this spinning up again another SageMaker processing job that you can watch. I think this one takes probably 10 minutes. Mine executed, so I can show you the result, and it generates another bias report, which you can download and check. So here you see how those metrics come back. And again, this is dependent on how the prediction results come back, right? So in our case, because we had little training data, the model picked up on a lot of 5-star ratings. So I guess many of those test predictions, right now come back with a high number of 5 stars. So there is some imbalances in terms, because we have not like perfectly fine, I guess, predictions here. And you can read up all of those specific metrics and what they mean. And pretty much what you end up doing is analyze, obviously, for your use case and for your data, what's kind of the acceptable range, and use this as a baseline. And then you can monitor your deployed models and detect any drift, for example, when the model starts to predict violating those baselines that you said are in the accepted range, for example. All right, so this was just briefly on using Clarify with the pre-trained model to check if there are any statistical imbalances you want to address. And another one here is the notebook number 10. Just briefly before we deploy it then in 11. 10 is also using SageMaker Clarify, but in this case, we're using the explainability feature. So what happens here is we're using the SHAP method, if you're familiar, maybe. It's also, we put in some links here, just scrolling down to the documentation to give you a little bit more background here on SHAP. It's basically checking which input features contributed to the prediction. And SHAP does it by, if you have 10 input features, using a subset of those, running test predictions, see the result, and then changing one input feature, like dropping one or replacing it by another, and check if the prediction result changes. So to figure out which feature really has an impact, right? The feature importance towards the prediction. So that is also helping to address the topic around explaining the model predictions. And there's just one more step here for the configuration that is actually setting this SHAP configuration. And I'll jump here to the report. In our case, it's not too overwhelming because we literally only pass product category and review body to the model. And here you can see actually the results that pretty much all of the importance is based on the actual review text rather than the product category. And this is kind of how we built the model here to really have the focus on the review text. But again, if you have a data set and training a model maybe with 10 input features, it would definitely be interesting to see how strong every individual feature is contributing towards a prediction. In this case, it's exactly what we want. We don't want to have the model being influenced, whether this is gift card or software, right? Really want to base, in this case, the prediction only on the actual text. So this is just briefly called feature importance, which you can also run using the SHAP method on your trained model. All right, 3 minutes left, and the last notebook here is deploying the model. So you have, in general, two ways to serve predictions. One is doing a batch job. So let's say you don't need 24/7 real-time model predictions, right? You might have data sitting in S3, and you need to run a job that is creating the predictions on that data. And this one you can use what's called batch transform for. What we're showing here is the other case. Let's say you want to deploy the model perfectly behind maybe a REST API, which you can then call from your application, microservices, etc., with the input data and receive a prediction back. So pretty simple, actually, using SageMaker. So we're pulling here the information, checking that the pipeline has finished, and we're looking up the model here. And if you remember, we cataloged the model as part of the model registry. So we're looking here at the model package that is actually holding the model. And we're approving the model package now to be deployed. So this is a manual step. You can also embed it in your pipeline. Here we're showing you how you can update this with a manual approval. So we allow the model to be deployed, and then checking the pipeline name. And what you need to do is really just to create the model, which we're doing here, and then creating an endpoint. So the endpoint specifies, if I scroll down here in the configuration, which instance types to use and how many. And then it's what SageMaker does is it will spin up those instances, in this case M5 for X large, and grab the pre-trained model, the model tar, which is output here of the training job, and if you have any specific model inference code, and deploy it together on that instance type, and also set up a REST API, which you can call to then get predictions. So if you scroll down, here's a deep link that takes you to the console, and it takes roughly 5 minutes to deploy the model. And in my case, I do have the model deployed, so you will see an in-service here. And with this, you can use this URL that is shown here. This is the API call to get predictions. And if I do this from the notebook, it's shown here. We can actually use a predictor coming here from the TensorFlow package, part of SageMaker. And then we're just sending in here some sample predictions. So this is great and this is awful, just checking how the model predicts and sending those inputs. And you will see here a result coming back from our deployed model through this API call. In this case, as I said, it picked up a lot on the fives with a limited data set and the gift cards, and it's returning in this case a 5. So this is how you can deploy a model as an endpoint and then use the API call to get predictions. All right, and we're on top of the scheduled time. I know this part has been a little bit quick, but again, thanks for your patience today. And we'll keep the environment up, Chris, I think for another hour at least, so you can go through those notebooks in a little bit more detail, and also if you want to rerun some of maybe the earlier notebooks, which you haven't done though, so feel free. And yeah, any last words, Chris?
Yeah, no, thanks everyone for being patient. I just posted all the links here to the book, to the GitHub, to the YouTube channel, and to the $25 credit code. So grab that. And yeah, thanks so much for staying with us.
Thanks, everyone.